Well, good morning and welcome. In our previous session, we discussed how a single independent variable could affect the optimum operation of a system. And now we're going to look at what happens when we have two or more independent variables. So for example, previously, the best cost was found according to the diameter of copper wire. But copper may well have alloying elements, and those will increase its electrical resistance, but also increase its lifetime. So both have an impact on the cost of operating our generating system, our transmission system, and therefore that cost should be optimized not only with respect to the wire diameter, but also the weight percentage of alloying element. So we want you to appreciate that usually two or more independent variables can affect the performance of an engineering system. You should be able to read those independent variables on a contour map. So if you're a fan of Ordnance Survey maps, you'll already be doing that. Also on a contour map, you should identify stationary points. In other words, on the OS map, you should be able to tell where a valley or a hill is. And we're going to introduce partial differentiation. So in the previous session, we differentiated y with regard to x, but there are now two independent variables or more, so we have to find slopes in two directions. So, and in the next session, we'll find where the stationary points are with two or more variables. But these are the slopes that we're looking for, and you'll notice that we'll have this partial differential operator. A very useful website which you might want to visit is the Maths is Fun website. So here's my Ordnance Survey map and a corresponding photograph. And I've highlighted a contour with red dots, and if I walk along this path, I am at constant altitude, constant height. So long as I go along here, I'm keeping a constant height. And you'll notice that there are lots of these contours. And these might be numbered in terms of height: 900, 910, 20, 30, 40, 50 meters. And the highest point is about here, and you can see it's fairly flattish in this area. So you can use the contours to find the highest point and also the lowest point. The contours cluster around here, conveniently marked by a patch of water. Now if I start at the origin and move north, I'm not climbing very much. So moving north, I don't cross many contours. The land is not steep, I have a shallow gradient. On the other hand, if I move east, I'm going down this very steep decline, almost a cliff. So I'm crossing contours very quickly. So I can also have contours on technical maps. Now this is an engine map, and you will come across these in your first year in the laboratory. And what I'm mapping is not height, but specific fuel consumption. SFC. And please ignore these lines which are moving from top left to bottom right. We're going to focus on these squashed circles. These are contours, and these are the lowest. These are contours of specific fuel consumption. On my y-axis, I have something called brake mean effective pressure. That's the average pressure in the engine. The bigger this is, the more work my engine does with every engine cycle. And on my x-axis, I have engine speed in revolutions per minute. So I'm moving very quickly, 4,000 revolutions per minute, about 80 miles per hour, and I have a pressure of 4 bar. You can see that my specific fuel consumption is 360. I'll just circle that. So I use 360 grams of petrol to do a kilowatt hour of work. You will find that the least specific fuel consumption is at this red cross. This is my red valley, and by I can see that I only need 235 grams of petrol to derive a kilowatt hour of work. So that is my best operating condition at 2,300 RPM and 8 bar. Now let's ask ourselves a couple of questions. If we fix our pressure at 5.5 bar, what then is the best operating speed, and what is the specific fuel consumption at that speed? So you can see that as I move along this line, I cut SFC at 260. Wasn't that annoying? I drew a line and it disappeared. Let's draw it again. So as I move along this line, it's disappeared again. I'll draw this by hand. I'm cutting the line at 260 and then 250 and 260 and 270. So the minimum is about here. So that's at 1750 RPM, and I'm using about 250 grams of petrol to do a kilowatt hour of work. Now suppose I would now fix my speed at 3,500 RPM. What's the best operation condition? Not down here, that's about 400 RPM, 290, 280, 280 again. It's about here between the 270 and the 280 contour. So this is my best operating condition, 8 bar, and I'm using 276 grams of petrol per kilowatt hour of work. So let's look at that as an analytical function, and I'm going to introduce partial differentiation. What's the slope? What's the slope? So here's my specific fuel consumption. I'm going to call it Z now. My speed, I'm going to call X, and my pressure. And my engine computer might want to know, if I change the rotational speed, RPM, what's the impact of that on specific fuel consumption? So this is called the partial derivative. And if I differentiate with respect to X, then I must fix my value of Y. So I operate on X, but I don't do anything with Y. And that gives my slope. And when that guy is equal to 0 at my stationary point, I'll notice that X is 2,300. Now I can take the derivative with regard to Y, and this time my function of X is fixed. X is treated as a constant, and I operate on Y. And notice that the max optimum Y is at 8 bar.